So what's the goal of the work is to try to improve the working condition in order to improve productivity and preserving workers' health, so to lower musculoskeletal disorders. So the idea is to use virtual reality to improve the ergonomics of workstations. So see the relationships between the user in the virtual world and the model of a working station. So virtual prototypes of working station before building this working station. And to do that, we tried to design a virtual arm in order to estimate and analyze muscle forces and postures. As you may know, for the moment, rules in ergonomics are mainly based on posture, and we wanted to provide a tool and to do some research on muscle forces during an activity. So let's try to analyze the process. The idea is to have a digital mock-up of a workstation, to have a user in virtual reality, to capture motion of the user, to deal with motion data, and to produce a motion analysis and diagnosis by means of a computer, of course. And the idea is twofold. With this motion analysis, we can imagine we can improve the the gesture of the user in order to perform the task with less damage or less musculoskeletal disorder. And the other point is to try to design a better adapted workstation, so to improve the ergonomics. Let's focus on this part of that is the core of the research. How do we go from motion capture to motion analysis and diagnosis by dealing with the motion data. So to do that, we proposed a biomechanical model over the arm. The idea is to have a kinematical model, to have here the ideal mechanical joints representing the model. It is, of course, a functional model and not a real model of what happens in the joints. It's idealized, and so it's more dedicated on functional anatomy than on real anatomy. Then, upon this model, we can build, so it's not so clear here, but we have the zoom on the right, a dynamical model. Here you have the joint position, you have derivative of order 2, so you can get position, speed, acceleration, and here go through the joint and compute the torques, and so torque and forces at the joint. So the idea is mainly here, it's a dynamical, classical dynamical model. To deal with muscle, we have to go furthermore in physiology. Or are the muscle attached on the joint, on the links? So here we have the case of the biceps, I think, if I remember well. You can see there A1 and A2 are the real point where the biceps, who has two links, is attached on the bones. But it's quite complex to deal with that, so we propose to have a sort of a mean of the action of the biceps on this action line that you see here between A and B. So we try to reduce the number of attachment of the muscles, so also in order to go to functional anatomy more than in the tendon, more than forces in the tendon, but more globally the action of the muscle. It's normalized by here the maximum effort possible for each muscle, and so here the idea is to use the arm level to compute here the muscle force, and we are coming to muscle force with on this based on this model. So let's recall, we go from motion capture. By motion capture we can obtain the orientation and position of all the segments. With invert geometry and the functional kinematical model we define, we can have a scaling model that's dedicated to the captured person, so the scale is taken here into account. When we have problems to deal with scale, we use the Leva table for this part, but also for dynamics part, let's mass, inertia, and something like that. We take that in the Leva table. And here, what's the output? It's the joint position associated with the motion. So on the real user, we can have a model, scaled model, with a joint position. The next step is to use this joint position into our dynamic model. Here it's inverse dynamic. Input is joint position, output is joint torques, and also forces in the joints. But these forces are taken into account also by the mechanical ideal model. So we are now to joint torques associated with the motion of the real user, and then we have to estimate the forces associated with the movement. So we try to minimize the action of each muscle with respect to the max action of this muscle. So this is a norm that we try to minimize, and we have constraints. The first one, for example, I think I have, okay, this is a cost function. I knew that I had a small animation. Here we have the mechanical equilibrium that's refer to the moment. The forces we have in the muscle are related to the torques in the joint, and the torques we have it from the step before. And here we have so it's related to muscular topology. Here we have the physiological parameter. The first one, for example, and the second one deals with a co-contraction factor. As you may know, we are over-actuated, and for example, for the elbow, if you want the elbow to be rigid, you have to contract the biceps and the triceps in order to maintain the rigidity of the articulation. So this is this co-contraction. The two antagonist muscles are used together to produce rigidity, and they are co-contracted. So it's this part of the physiology. And here it's simply not to overload the muscle and not to be over the maximum forces it can develop. So with this minimization under constraints, so we solve that with a minimization algorithm, we obtain the muscle forces associated with the movement. Let's come back to physiology again, just to have a focus on co-contraction. So here you have the elbow flexion, the angle of the elbow, and the ratio between flexor and extensor in the elbow. So if I remember well, biceps and brachialis are flexor and triceps is an extensor here, and we obtained this co-contraction alpha co-contraction ratio with open seam. After that, once we have this efforts in the muscle, we define a mean muscle activity. So it's how we use our muscle during the activity. Let's recall the real user is doing a real activity, but he is in the virtual world, but the activity is real. And this mean muscle activity with this dynamical tool will be compared with the ruler classical score, that is a postural tool used in ergonomics. So let's see how it is. So here we have a model. It's just to propose the motion. We present that to the user here for a flexion extension because we remarked that we are very good to follow a prescribed trajectory by a visual input. So we have this guide. And then we have the outputs. This is here the elbow position, here the mean muscle activity, and in green the postural criterion. So you see discontinuities. 2 is not comfortable, 1 is more comfortable, 2 is not comfortable. And the idea is to try to use the mean muscular activity to give new indicators not related to posture but to muscle activity. So here we have the record. Let's go to the following. So we did some comparison. I will not go in details here. Just it was what I wanted to show you what we do in ergonomics. We had the opportunity last week and the week before to welcome a TNA. So it was named VRGO for ergonomic in virtual environments. One colleague from the Center of Sensory Motor Information of Aalborg University came from June 25th to July 6th, so 2 weeks, and it was last week and the week before. And the idea was to compare virtual environment versus a real setup with respect to changes in the movement pattern and to muscle fatigues. So to do that, we had motion capture and kinetics, kinematics, and dynamics. That is not treated for the moment, but we will use what I presented before to do this treatment. And the second part, we record also surface electromyography. That is an image of the muscular activation. So the idea is to use motion on one side and electromyography on the other side to see if motion, to explore the relation between motion and muscle activation. So it will be very short. I have just some pictures to show. So here it is the equipment. We see this is a colleague from Aalborg. We see here the motion capture, and here not clearly, but the links to the computer for recording electromyography, surface electromyographic signals. We compare real tasks. Here you have a real workstation. So the idea is to take an object here, to put it in here in the box, which is dedicated just as a Kinder box, where we can have forms that fit or do not fit into the holes. And if it fits, it's inside. If it doesn't fit, you put it here and you put it aside and you take another one here. So this is a real workstation. Here we have a zoom to see the electromyographic device here on the shoulder, and here's the motion capture tool. The other part was to do that with here on the picture. Of course, we cannot see that it is colocalized, but here the picture, it is colocalized, so the position of the workstation is positioned with respect to the head tracking system of the user. And here the manipulation is with a fly stick. And then we tried also with an haptic device to see if haptic feedback helps or not doing the activity and changes or not the motion during the task. So we have a virtual, real setup, a virtual without haptic, and a virtual with haptic. And the idea is to have the recording of the motion capture in all the cases and the recording of electromyographics signals in all the cases. Just to say, we had 15 users who tried this experiment, and as it was last week, we have no results, of course, for the moment. So thank you for your attention. No, it's much more the context that we wanted to present here. We have no formal approach. What we want to do is to concentrate on the right parts here. So to show that it is possible to improve ruler methods with biomechanics indicators, but we are not able to build the indicators. We are able to give the analysis that will allow some specialists in ergonomics and motion to build indicators that are relevant. We have ideas, of course, but I think the end of our work is quite on this part. It's also why we wanted to work with Halborg, because they are biomechanical scientists and know very well how to manage this information, this muscle forces information to have consequences on the indicators. So this is the first point. And the second point is clearly here, redesign of virtual workstation. We have no automatical process, but as you know, in virtual reality, we deal with digital mockups, so we can change some parameters, and it was the idea also we had in the TNA to have the real workstation. We can change the parameters. We can change the height in this case, in this particular case, and we can do the same thing in the virtual world. And the idea is to compare virtual versus real, and maybe we will have some rules that will be useful in this case, but once again, we have no direct method or methodology. It's just using know-how. And what concerns the user, we imagine that we could use this kind of tool to say to you, user, you should do this motion because it will be less painful than this motion. And here we have people in the team who are working on sport and rehabilitation, and certainly could use the results of our break to perform some training of the user with respect to a virtual workstation. So this is the idea, but clearly what I shown is this part is how we can access to muscle forces, and this is we have ideas on this part of improving work task gesture and improving workstation, but no systematical approach on this domain. Here you have the real setup, and here you have the virtual setup, and the CAD model for the both is the same. So we started with a CAD model, and we had the export in VR here, and here we had building of the setup. So it's just bars and screws, but we can set the height here. We can also set the height of the tablets here, move around these bars. And so the idea was also to have the same CAD to see if during the design process we can export a real setup, a virtual setup, and compare the two with the same CAD as a starting point. So it was clearly what we wanted to do. Something I didn't say, I think it was somewhere here. This part of the algorithm is very time consuming, but we can at this point store the results of a lot of motion cases into a database, what we did also. And so we use, when we want to curves, for example, we can either minimize, so it's offline, but if we have enough motion, if the motion are representing well the set of motion we want to test, we can use the database, and then we have interpolation processes into the database that are in real time. So this is the second part I didn't present, but that Charles had in his PhD also. So it was the idea. It was not completely validated, but it was the idea we tried to push, and we continue to work on this part now also. Here the TNA is to try to validate muscle forces. So to validate this minimization algorithm that produces joint torques, but to validate them by a direct approach with activity of the muscle by electromyography. So it's another way to close the loop. It's closing the loop between motion and activation. So this is what we are working on at the moment, but we have also ideas, and we had some propositions in terms of a database on interpolation into within the database to achieve real time, such as RULA can be, because RULA is very easy to put in real time, and this kind of minimization is quite more difficult. So the idea was to store enough motion, so to have a database of treated motion to use them in real time. So we did that also. We try. It's not finished on this part, but we had some we have some ideas, and it certainly will continue on this direction in the future.